happy to introduce our last speaker of the day in the workshop, James Drummond, who is at CERN at the moment. We'll talk about symbols and bootstraps for scattering amplitudes at higher and higher loops.
Okay. Well, thank you very much to the organisers for organising this very nice workshop. Let me just describe a little bit about the setup of what I'm going to describe. We're interested in scattering amplitudes, of course, at this workshop, and we've heard a lot about various aspects of those, and some of those aspects already today, which are going to come up again in this talk. Let me just sketch the very basic setup, which we've already heard a little bit about. But we're going to consider some endpoint scattering process. So I'll put some momenta coming in, P1, P2, and so on. And these are, of course, light-like momenta. So they're null. We're considering scattering of massless particles. And we're going to be considering the planar n equals 4 gauge theory in particular. And as we all know, since these are massless particles, we can factorize the momentum pi in terms of two commuting spinors, lambda I, lambda tilde alpha dot. Lambda tilde I alpha dot. Okay, so that's the kinematics of the situation that we want to describe. The scattering amplitude, they're functions of these variables. And the simplest scattering amplitudes that we're interested in are the MHV amplitudes. So the amplitudes are not just functions of the momenta, they also depend on the helicity or assignments of the incoming particles. So I can assign helicities plus or minus 1. And the MHV, these are the amplitudes that have, let's say, 2 minuses and all the rest plus. These are the simplest. Any more pluses and the thing vanishes. And the next to MHV, well, these will be 3 minuses and all the rest plus. And then you can go to next to MHV and so on. Those are the two that I'm going to discuss in this talk, just the simplest and the next to simplest, if you like. And in particular, I'm going to discuss amplitudes at 6 points. So there's a good reason to discuss 6 points, which I will illuminate, but let me just sketch somehow the available amplitudes in the theory. So if we think about the number of points, if n equals 4 points, then we only have an MHV amplitude. There's a single amplitude that's worth considering. If I go to 5 points, then I have an MHV amplitude, which I'll draw here, and its parity conjugate, the MHV bar amplitude. And if I go to 6 points, then I'll have an MHV amplitude, its parity conjugate, and some new amplitude, which is the next to MHV amplitude at 6 points. And parity is somehow a reflection in this axis of that diagram. So this axis are the MHV amplitudes here. This axis, you can say, are the next to MHV amplitudes. So for 6 points, MHV and next to MHV cover everything. This is just the parity conjugate of MHV again. For 7 points, of course, you can higher, you can have more in the game. But for 6 points, this is all we're going to describe. So we just need to look at MHV next to MHV. And why 6 points? Well, for fewer points, the 4 and 5 particle amplitudes, those are essentially fixed to all orders by symmetry. So the symmetry that fixes those is dual conformal symmetry. We've heard already a description of how that appears in the theory. So that this symmetry is something that fixes the 4 and 5 particle amplitudes, but it doesn't fix the 6 particle amplitudes and beyond, which is why these are the interesting quantities to study. So in the end, what we end up doing is describing functions of invariance under this symmetry. So in other words, there are invariants under this symmetry, so there's something for these amplitudes to depend on, non-trivially. Okay, so let's just, let me just sketch for the MHV amplitudes very schematically. I can write this function as its tree level part. You can factorize this out, and then I will multiply that by something which I will write in the exponent. So it will be the exponential of, well, there will be some universal infrared divergences, which I'll just denote by IR divergent, and then some finite piece. So this is the interesting function that we'd like to understand. So the IR divergences are somehow canonical and known, and this function is the thing that we'd like to understand, describing the non-trivial dynamics entering these scattering amplitudes. And dual conformal symmetry tells us some constraints on the form of this finite piece. So let me just sketch. We already saw from Paul's talk earlier, and also from Lionel's talk, I think, how to think about this, but the central relation is really just to replace the momenta by differences of some dual coordinates. And in order to make sure I get my momenta pointing the right way, I'll define them this way. So in that case, let me write, so P1 will be the difference of x2 and x1. So let me draw some polygon. That's what I obtain from replacing momenta by differences of coordinates. So the momenta now will be lying on the edges. This will be x1, this is P1, this will be x2, x3, and so on. And since the momenta were light-like, then the corners of this polygon are light-like separated. So that's just some change of notation, if you like, a change of variables. Now this polygon closes due to momentum conservation, so this change of variables actually trivializes momentum conservation. So it solves one of the constraints on the momenta, because of course the amplitude always has a momentum conserving delta function. So now with this change of variables, it makes it rather clear that you can think about these x's, which are describing the momenta, as coordinates in some space, in fact the corners of this light-like polygon. And it then becomes natural to consider transformations acting on those coordinates. In particular, you can consider the space of conformal transformations. And the conformal transformations leave a light-like polygon, map a light-like polygon into another light-like polygon. So it's a natural thing to do. And so conformal transformations of the xi's, this is from the point of view of the amplitude, dual conformal symmetry, dual conformal transformations. Now, this map isn't just about the symmetry. In fact, this object here, this light-like polygon, is of course associated with a Wilson loop. You can consider the Wilson loop on this contour, the integral of the gauge field, path-ordered integral of the gauge field around that contour. And that's an object in the theory which manifests this conformal symmetry. It's a natural symmetry of that object. And moreover, this scattering amplitude and this Wilson loop are actually related to each other. So therefore, the scattering amplitude inherits this conformal symmetry of the Wilson loop, and it becomes a bona fide symmetry acting on this function f, which describes the scattering amplitudes. In particular, you have, let me write the generator of conformal transformations. You have the first order differential operator. So that's the generator of conformal transformations on the x's. And the effect of this conformal symmetry, or dual conformal symmetry, depending on your point of view, if you're an amplitude or a Wilson loop, is to give you a Ward identity for this function f. So it's a first order differential equation, which takes the following form. You have some prefactor, which is given by the cusp anomalous dimension, which is a function of the Toft coupling A, and then some universal kinematic dependence, which takes the following form. It's rather simple. So it's just this combination of x's times the logarithm of the only non-zero distance in the game of those 3 points, I minus 1, and I plus 1. That's the only non-zero one because these neighbouring points are like separated. Okay, so you have this first order differential equation, conformal ward identity, and now it's clear that it's going to fix the 4 and 5 particle amplitudes because there are no conformal invariants that you conform with 4 and 5 points due to these light constraints. In fact, the first, let me go to this one. So the first level where first time we encounter conformal invariance is for n equals 6, and in that case there are 3 of them. Let me write it as x13 squared, x46 squared over x14 squared, x36 squared, where this is obviously this is x1 minus x3 all squared, and 2 rotations of that. I'll call them v and w. So there's u, v, and w, the 3 conformal cross ratios. So there's 3 variables available at 6 points. There are no variables available at lower points, and so below 6 points this equation uniquely fixes f up to a constant, but from 6 points and beyond it fixes f up to a function of these variables. So we have f is going to take some form, there'll be some piece which is we can call the BDS part, has a prefactor of the gamma cusp. It has some universal function which you could in principle determine at one loop. This piece just contains things like log, and dilogarithms of Mandelstam variables. And then the piece that we're interested in this talk, there will be some so-called remainder function denoted R, which is a function of these conformal invariants, function of the ui. And that starts being non-zero at 6 points and beyond. Okay, so that's one of the the objects that we're interested in this talk. So-called remainder function. Okay, and we heard from the previous talk that there's a very nice analytic form for that now known at 2 loops. So this is known explicitly to 2 loops. So in this talk what I'm going to be discussing is how, given that data, we might generalize what we learn by looking at its form and extrapolate it to higher loops. In particular, we'll look at 3 loops. So we want to take this and go to 3 loops. Okay. So now, since I've just been discussing dual conformal symmetry and the cross ratios, it's a good opportunity to introduce some other nice variables which show up in the game, which are very convenient for analyzing the structure of this function. So let me introduce momentum twisters. So here what I'm going to do is I'm going to take, so we had the momentum pi, I'll just take the first half, this lambda variable, so I'll form an object wi, which is lambda I and then xi contracted with lambda I. And this is now a 4-component object. This is the first 2 components, and this is the second 2 components, so this is 4 components overall. And it transforms linearly under these conformal transformations or dual conformal transformations, depending on your point of view. So this is just has an SL4 index and transforms linearly. So that means it's very convenient to use these variables to write down invariance. In particular, invariance are just the antisymmetric contraction of 4 of these guys. It's just epsilon A, B, C, D, Wi, A, Wj, B, Wk, C, WLD, or 4 brackets just denoted by the symbol IJKL. Okay, very good. In fact, well, so if we look at now, if we're thinking about these x variables, if we have some difference, xij squared, xi minus xj squared, that effectively translates into the 4 bracket with neighboring pairs, I minus 1i, j minus 1j, up to some additional factors which are going to be irrelevant here. So that's sort of how we can translate between the language of the cross ratios in terms of the x's into these 4 brackets. And moreover, in fact, for 6 points, which is what we're going to be interested in this talk, we can even simplify further. And we can say, well, since there are only 6 momentum twistors available, an antisymmetric combination of 4 of them, I might as well just denote that by the 2 which are missing instead of the 4 which are present. So I'll replace, say, 1, 2, 3, 4. I'll just denote that by a 2 bracket, 5, 6. Okay, that just compactifies the notation, and it sort of makes it clear that the kinematics, the kinematics of this scattering amplitude are really just determined by 6 points living in CP1, or 6 complex numbers, modulo SL2 conformal transformations. So we're just looking at conformally equivalent configurations of 6 complex numbers. Okay. So in that language then, the cross ratio will end up, U will end up being just 2, 3, 5, 6 over 2, 5, 3, 6. And you can see here, so these in principle are 2-component objects, but I said they're just complex numbers. What I really mean is that you have to mod out by a scaling transformation in these 2 components, and that's done here by forming a homogeneous combination. So you see 2 appears in the numerator and the denominator. Similarly, 3, 5, and 6. So U is a good, homogeneous, invariant combination of these variables. And what's particularly nice about that, so of course, given U, I can form V and W by doing rotations. And if I do a 4th rotation, that takes me back to U. So these things are obviously related by just cyclically rotating the data. So that's the cross ratios. But I can also consider 1 minus cross ratios. That crops up quite often as well. And these things also have a very nice form, because in fact you can use some cyclic, you can just take 1 minus this, use some cyclic identity to simplify it, and it will take this nice factorized form as well. Same denominator, different numerator. And similarly, I can obtain 1 minus V, 1 minus W by cyclic rotations. Okay, so that's good. And then, given U and 1 minus U, there's another set of variables which I'm also going to write down in terms of these 2 brackets. And let me write them here. So that's going to denote those by YU. YU is something which involves a product of 3 of these brackets in the numerator and correspondingly 3 in the denominator. It's also homogeneous. And then given that, I can then obtain by cyclic rotation YV. Actually, I'm going to define the cyclic rotation of this to be 1 over YV, and then cyclically rotate again. That will be YW. And if I on this occasion, unlike for the U's and the 1 minus U's, if I rotate again, I obtain 1 over YU, and I have to go through all 6 times to come back to YU. That's the difference between the Y's and the U's and 1 minus U's. Okay. So these are sort of 9 nice variables which are going to be very useful in parameterizing the kinds of functions that we want to describe in this problem. for the 6-point amplitudes. Okay, and so I should maybe point out that these y's, from the previous talk we heard about the two-loop remainder function. So this function described at 2 loops can be written in terms of polylogarithmic functions whose arguments contain square roots of the cross ratios, of particular combinations of square roots of the cross ratios. So these y's are essentially those square roots written in some useful way. So yu will be this combination u minus z plus over u minus z minus, where z plus and z minus, z plus and minus will be a half minus 1 plus the sum plus or minus square root of this quantity delta, where delta itself is equal to 1 minus the sum all squared minus 4 uvw. So these formulas, I just showed these formulae because these will be familiar to anybody who's read the Goncharoff, Spradlin, Virgil-Volovich paper on the two-loop remainder function. The y's are they? Well, they're very convenient because they factorize in terms of these two brackets. So jumping ahead a little bit, they're going to be very useful for parametrizing the symbol. So if you take the symbol of this two-loop remainder function, you will find that you can write it in terms of, you can write it in several ways, but a very useful way for us for writing it is in terms of these 9 letters, u, v, w, 1 minus u, 1 minus v, 1 minus w, and yu, yv, yw.
So the z's don't do that?
The z's themselves, no, I think you always need a bit of decoration. Yeah. Yeah. Some entries you can just write in terms of the z's. Okay. So, okay, very good. So that's sort of classifying the kinematic problem and writing down the quantities which I'm going to want to use to describe it. Now let me. So that's, so far we've discussed MHV. So let me describe a little bit about what happens for the next MHV case. So all of this, of course, will still be relevant because we still have the same, we have dual conformal symmetry, you're going to have functions of these cross ratios and so on. But in addition, we have to describe a little bit about how the helicity structure enters. And the nice way to do this is to introduce an on-shell superfield, which is just a function of some Grassmann parameter, which contains all the on-shell states of the theory. In particular, it starts with the on-shell gluon, and then is expanded in terms of these Grassmann variables, which transform in fundamental representation of SU4, which I'll denote by A prime as an index. So, in particular, here I'll have the positive helicity gluon, these will be the gluinos, there'll be scalars, etc., all the way up to the e to the 4th component, which will be the negative helicity gluon. So all the particles in the theory, all the on-shell states of the theory can be described by this superfield. And then, if I want to describe now amplitudes with arbitrary helicity configurations, I should just consider scattering of these superfields. Okay, so the object I want to consider will be some amplitude of phi 1 up to phi n. And then when I expand it out in terms of these eta variables, I can pick any component I desire. Now there's also an analog, having introduced these Grassmann variables for the supersymmetry, we can attach them to these momentum twisters as well. So to do that, let me introduce the analog of the dual x coordinates in terms of fermions. So what I have to do is introduce some theta coordinates, And I'll say that the difference of these two chiral dual thetas is equal to, whereas for x's it was xi plus 1 minus xi is lambda lambda tilde, which was p, the momentum p. Here it will be lambda I eta I. So I'll take the same lambda from here, but then I'll also attach this Grassmann parameter. So this is the supercharge associated to each of the particles. So the fermionic partner of the momentum. Now, given these thetas, then I can do the analog of this here and obtain a, how will I call it, some momentum super twister, which will be the lambda I and the xi lambda I as before. And then in the fermionic sector, it will be theta I lambda I contracted. And this now transforms under SL4/4. So it's a 4/4 component object. Transforms linearly under SL4/4, which is the superconformal algebra. Okay, so that's very good. Now, what happens for the next MHV amplitudes, or the non-MHV amplitudes, is it's very convenient if I factor out, now for the full superamplitude, I'm going to factor out the MHV part and then describe the rest by what I have to multiply that by in order to get the right answer. And this thing therefore will start with 1 for the MHV part, but then for the next MHV part, this is the piece, the next term, which will have 4 of these Grassmann variables. So this has none of them, obviously. 1 has no Grassmann variables. And then I can continue. There'll be next to MHV and so on. But the interesting quantity from the point of view of the 6-point amplitudes is just the next to MHV. So that's the second interesting quantity that we're going to look at in this talk. And this is called the ratio function. Okay, so we're interested in remainder for MHV and the ratio function for next to MHV. And this is only known to one loop. Or at least before our analysis. And now let me describe a little bit about its structure. So I think I will go, maybe I'll go up here. Okay. Okay, so given these momentum supertwisters, you can form these useful quantities, which are antisymmetric combinations of 5 momentum supertwisters. And Lionel introduced these yesterday, but let me remind you the explicit formula. I'm going to call this quantity here chi. So this will be a 4-dimensional fermionic delta function of chi1, and then the 4 bracket 2, 3, 4, 5 plus cyclic divided by the product of the 4 brackets running cyclically up to 5, 1, 2, 3. Okay, so that's a completely antisymmetric combination of 5 momentum supertwisters. And these things are called R invariants because, well, the invariant in particular because they're invariant under, well, dual conformal symmetry is manifest, but also under, in fact, dual superconformal symmetry. And even, in fact, the full Yangian of that algebra. And these things then enter the ratio function in a particular way. So let me write this P n MHV. In the following form. I'll have some function v1, And then that will come with a particular combination. So let me also shorten this notation. If I have an antisymmetric thing of 5 momentum twisters and I've only got 6, I'll just denote this by the one that's missing again. So if I use that compact notation, then here I'll have 2 plus 5, plus cyclic combinations. And in principle, I can also have 2 minus 5. Now the reason I do this splitting, the splitting up, is that there are sort of 2 sectors to the amplitude. I can form this sort of even combination multiplied by a parity even function, v, and this odd combination multiplied by a parity odd function, v tilde, and then take the 2 copies of that each time. So there's sort of 6 chunks that are related by cyclic rotation, but they come into 2 groups which are not obviously related to each other. Okay. So now, as I said, these functions, well, at tree level, let me say, the tree level, the v's are basically 1, and the v tildes are 0. And at one loop, the v's contain very much like the one loop MHV amplitudes. They contain log-logs and dilogs, this time of conformal cross ratios. So these are simple functions. And so we're interested in understanding whether or not we can bootstrap that up to 2 loops. And in a sense, 2 loops for next to MHV is very much in the same level of complexity as 3 loops for MHV. Although being 1 loop lower in terms of the complexity of the functions, actually we'll be able to say a bit more in that case. Okay. All right, so that more or less sort of narrows or pins down the objects that I want to consider at the level I want to consider them. So let me describe a little bit about our strategy for understanding their structure at higher loop orders. So one thing that crops up all over the place in planar n equals 4 is the notion of transcendentality. We heard about this from Paul earlier today, and also from Nastya in the previous talk. So we're going to adopt this observed behavior as one of our assumptions. So it's an assumption about the analytic properties of the relevant functions in the game, the function r and these functions v and v tilde. So what is how to formulate the assumption? So we're going to look at functions which we call pure, or you can call maximally transcendental, or iterated integrals, or Goncharov polylogs, or various other names for them. And specifically, there are things that come with a degree, so degree k, and for us the degree k is going to be equal to twice the loop order, so k equals 2l. In other words, it's going to be degree 6 for the 3-loop remainder function and degree 4 for the 2-loop next to MHV ratio function for v and v tilde. So, but more generally, for a function of degree k, it's something who, when you take its derivative, it's always expressible in terms of functions finite sum over functions of 1 lower degree times d log of some algebraic function phi r. So phi is algebraic, the sum is finite, and since this is a recursive definition, I should say that the f the only function of degree 0 is a rational constant, our rational constant. In particular, it then follows that the only functions of degree 1 are logarithms of some algebraic function. And the only functions of degree 2 are products of logarithms or the dilogarithm of some algebraic function. Okay, that's very good. So this is not an innocent assumption, but it's something that works so far. Now, given this, we also heard in some talks today, we can define the symbol. So the symbol is something that's extremely useful when you don't have a handle on the actual function that you're talking about. In fact, you may not even have a way to write down a function of all the variables that you're interested in of the right degree. But even if you don't, you can write down, you can talk about its symbol. And the symbol of function of degree k is defined recursively following this formula. So I write the same sum, the symbol of these frk minus 1s, so the symbols of the functions of 1 degree lower, tensor the argument of this logarithm, phi r. Okay, so this is something that captures some analytic information about the original function, but it loses some information as well. In particular, since this is integrating up, you lose constants at each stage of this differentiation process. Okay, so it's maybe worth making some comments about those assumptions. Do that. Yeah. So, well, before I say that, let me just make another assumption about which concerns the symbol. So we're going to assume that the functions appearing have a symbol, essentially. Moreover, we're going to assume that the symbol takes the form of a sum of terms, each of which can be written in terms of these two brackets that I like to introduce. So it's a sum over, so degree k, so there'll be k entries in this tensor product. Each entry is sum 2 bracket, and then a sum of terms like that. Okay? So, or alternatively, this is equivalent. Given that we have homogeneity in these 2 brackets, it's something, the symbol, whose elements are drawn from this set of letters that I wrote down up here. So there's u, v, w, 1 minus u, 1 minus v, 1 minus w, and then the y's. So there's these 9 letters. And the reason there are 9 is, as I described before, you have 15 2 brackets, 6 choose 2. And then you have 6 homogeneity conditions. So the functions should be homogeneous in scalings of each individually. So that leaves 9 homogeneous combinations. So these are the 9 homogeneous combinations, and we're assuming that the symbol, its entries, i.e. the arguments of the logs at each stage of this reduction, can be written in terms of, are just these variables. Okay. So, so 1 is not a very innocent assumption. There are other functions. So but up to 2 loops, this is certainly sufficient. And we'll see that it's consistent also at 3 loops. But given 1, 2 is very natural, at least for 6 points. And the reason is simply that, as we described before, 6-point kinematics is really just described by conformally equivalent configurations of 6 points, 6 complex numbers. And the only thing interesting that can happen is when 2 of them coincide. So singularities should be to do with when 2 things coincide, and that's exactly when one of these guys vanishes. So the locations of singularities are somehow encoded in the entries of these symbols. So that's why, at least at 6 points, this assumption 2 is very natural from the point of view of analytic structure. Okay. And another point is, so not only is it these 2 assumptions are consistent with, let's say, everything we know, in particular the known 2-loop remainder function described by Goncharov and collaborators that we heard about in the previous talk, but also, in fact, no known loop integral, and we can evaluate several loop integrals, in particular for 6 points. So any integral that we have a handle on, for example from differential equations, also obeys this structure. This is at all of course, this is at 6 points. Okay, so it's really very natural, just generically, from the structure of functions that you can have in the game at 6 points. Okay. So then what do we do? How do we proceed practically? We have some idea of the class of functions that we want to write down. We've got this notion of the symbol. So we just write down the most general symbol that you can possibly imagine of a given degree, say degree 6 for the 3-loop remainder function, made up of these letters. And then we start thinking about what constraints it has to satisfy. So let me go up here. So what constraints should the symbol satisfy? First of all, the symbol should actually describe a function. So if I write down just a random tensor product with a bunch of letters, we've heard earlier that this is not something that necessarily is the symbol of a function that you might have started with. In particular, you have the obvious constraint that d squared on any function has to identically vanish. So that imposes relations amongst the various terms that you can write down here. This really becomes powerful, should probably stress that this becomes powerful when you have variables which really couple different variables up to each other. So if I stopped here and I only allowed myself these 6 letters, then it's very simple to write down integrable symbols. Integrable symbols will simply be products of single variable, symbols of products of single variable functions. So, and for single variables, this is not a constraint. D squared will vanish identically on any symbol which only depends on u, say. But this really comes into play when you introduce something which actually couples up, in this case, these 3 variables in some non-trivial way. And remember these y's, there were some complicated square roots depending on all 3 variables simultaneously. So, in particular, what's nice about it is you can write down the symbols obeying this condition even without any formula for that class of functions at all. So you might not have any integral that you know, which has a symbol in this class, but you can still discuss all of these functions. Okay, very good. So that's one universal constraint, just so that we're talking about actual functions. And then another constraint, which is a physical constraint, should be that the discontinuities in these functions, which are basically 2 particle cuts, they should only appear when one of these xij squareds, or equivalently an adjacent sum of momenta, p1 plus p2 plus p3 all squared, say, vanishes. So this is the only allowed locations for these two particle cuts, right? Because I have some ordered amplitude, I do some cut, and then I have some ordered set of momenta on the left and an ordered set on the right, and I expect to get branch cuts when I take a cut of that form, but not some other random variable. And that means that the initial entry of the symbol can only be actually one of the first three in this set, only u, v, or w. Okay, the others are not of that form. And the first entry of the symbol is what tells you about the discontinuities of that function. Okay. So now, if we look at the MHV remainder function, this R function, then there are a set of constraints which are particular to that. I have, for example, permutation symmetry in U, V, and W. It should be parity even. And that means an even number of entries involving the y's, because the y's invert under parity. So if I have an even number of them, the function will be parity even. There should be a vanishing collinear limit. So if I take two adjacent legs going to be collinear, or equivalently from the Wilson loop picture, if two of the legs are becoming collinear, then I expect R to vanish. And then there's an additional constraint that we employ. Well, we don't have to employ. We can analyze the consequences with and without it. But let me go here. But we had a constraint on the initial entry of the symbol. You can also impose a constraint on the final entry of the symbol, which is a constraint on the form of the derivatives of the function that we're interested in. So let me write down just the constraint. We're interested in the following variables. So we insist that the final entry is drawn from this set of 6 letters, which doesn't violate the original set because this is a ratio of 2 of those letters. So when you have a ratio of 2 of those letters, as Paul and Astio explained before, you can just you can factorize this element and write it as a sum of 2 elements in the symbol. And this constraint here, this comes from, well, from various sources. There's a conjecture by Simon Caron that the analytic structure, essentially the analytic structure of the remainder function combined with supersymmetry should tell you that the final entries should be of this form. We also observed this actually in the form of the loop integrals that we can analyze via differential equation, and essentially the final entry is restricted to be of that form so that the integral does satisfy its differential equation. And more recently, there's been this idea of a sort of a Q-bar bootstrap we also heard about, from which you can look and see that if you analyze that in some detail, it will tell you something about the final entries of the symbols of the functions you're trying to construct. So there's some relation to Q-bar, let's say, which is telling you about the derivatives of this function. Okay. So, well, there's an analogous set of constraints that we impose for the next to MHV ratio function. Let me not enumerate them all. Let me just go to perhaps what's the most important constraint of all for our point of view, which is the OPE. So we have the idea that we can analyze these functions either as scattering amplitudes or as Wilson loops. And so if we think about this thing as a Wilson loop, there's a constraint coming from the fact that I can expand a Wilson loop about a sort of a vacuum configuration, which is a square, a light-like square. All the edges are light-like. And I think about this Wilson loop being expanded about the limit where two edges become collinear. So the vacuum is the square, and the expansion is an exchange of states which takes you away from the square. So in particular, you can write this thing as essentially a sum over exchanged states with some form factors, with the exponential of the energy of that state times tau, where tau is the parameter which is governing how close you are to this collinear limit. There's some parameter in the configuration which is taking you to the collinear limit. That's tau goes to infinity. So this is collinear limit is tau goes to infinity. And there's an expansion over states which are exchanged, which have certain energies under eigenvalues under the tau scaling. And in general, En, of course, is going to be a function of the coupling. So it's going to have some En0 plus g squared corrections, En1 plus g to the 4, En2 plus dot dot dot. There'll be an expansion in the coupling. And that means then that this gives us an integral dn Cn, if I just do this Taylor expansion, e to the minus En0 tau times, now I expand out the exponential, and I obtain 1 minus g squared tau, I bring down a tau from the exponent, times the first order correction, En1. And then there'll be g to the 4, and then the g to the 4 thing will come with, there'll be a term which is tau squared, which comes with En1 all squared, and another piece which is just tau coming with En2, and so on. And the important point about this expansion is the piece that has the leading power of tau at any order in this expansion is always governed by some power of the one loop correction to the exchange state energy. So if you only know the one loop energy of a single particle state being exchanged between the bottom and the top, you can actually read off a piece of the amplitude, which is the leading tau power in this near collinear limit to any loop order. And the leading power of tau is exactly the leading discontinuity So leading power of tau corresponds to the leading discontinuity in one of the cross ratios. In let's say, the cross ratio V. And tau here, of course, the configuration of the Wilson loop is given in terms of u, v, and w. It's also given in terms of, let's say, tau, sigma, and phi. Tau will be related to, V will be related to tau by 1 over cosh squared tau. There'll be some complicated formulas for u and w in terms of tau, sigma, and phi. So some change of variables in the game. But in particular, this leading power of tau, it tells you about the discontinuity in one of the cross ratio variables. And for r, the remainder function, for example, it doesn't even matter which, because it's completely permutation invariant. Okay, so let me just be slightly more precise about that. So I'll write down an example which is for the next to MHV, let's say the 2-loop next to MHV ratio function. There'll be a sum over Fourier modes in the other two of these variables. There'll be sigma and phi as well. Tau, sigma, and phi are just tau is the scaling in this direction, sigma parameterizes the scaling in that direction, and phi is the angular rotation, which doesn't see the square at all. So that's sort of a way of thinking about what those three variables are. And they're just a remapping of u, v, and w. So if I write an expansion in Fourier modes in these variables, then I'll end up with some expression of this form. Where here, so these are some form factor associated to these C's that I schematically wrote there. The F organizes the states into some conformal towers. You can think of them as conformal blocks. So it groups a bunch of exchange states together with a primary with its descendants. And then here's the anomalous dimension, this gamma m of p squared, which comes in. Okay, so it's the one, if you like, it's the one loop anomalous dimension to the power 2. In fact, all we really need in order to do our analysis is the form of this expression, because the form of this expression guarantees the fact that it comes out. What this expression is saying is you can organize your expansion in terms of conformal blocks of exchange states. So from that it follows that there's a differential operator which annihilates this sum. And it annihilates this sum. It doesn't even care about the details of what these quantities are. Well, it cares about the details of this f, but it doesn't care about the details of these other bits. And this d is some second-order differential operator. I'll write it out explicitly so you can see it's really not complicated. So that's some differential, a second-order differential operator, which annihilates this double discontinuity. However, we have an ansatz for the symbol of the function that we're interested in. And we know what the discontinuity means. The discontinuity means, if I look at the symbol, I just peel off, if I'm interested in the discontinuity in V, I just look at the part of the symbol that begins with V, and then what's sitting behind is the symbol of its discontinuity. If I'm interested in the double discontinuity, I do that twice. So the double discontinuity then from our ansatz will just be something that's 2 steps shorter, and then again a sum of these terms involving these 9 letters. So we have some explicit expression within our ansatz for the double discontinuity. And then all we need to do is insist that it takes an OPE form. We don't even need to insist on the explicit OPE form. And that it takes an OPE form means it's annihilated by that operator. And then within our ansatz, that's essentially sufficient to fix the leading discontinuity, at least its symbol. Okay. Okay, so that's more or less the, I won't go into any more details of the method. Let me just now summarize what we obtain. So the end result of this process is the following. So let's imagine now, well, let me say what we get for the 3-loop ratio function, 3-loop remainder function, the MHV case. In that case, we find that this symbol is actually fixed. So there's some symbol x of x X is a piece which has a double discontinuity and therefore is fixed by this OPE constraint. And then in addition there's two ambiguities, F1 and F2. And these are two pieces which have no double discontinuity. And so they can't be fixed by this analysis. So that's really quite constraining. Within the ansatz, there's essentially a two-parameter space only of functions which obey all these constraints that we're imposing on them.
What's the definition of that V? And how do you know the double discontinuity when reconstructed before?
Within the symbol, the definition of delta V is you just take the piece of the symbol that has V in its initial entry and in its second entry.
Opposite to entry.
Yeah. And then what's left behind is the symbol of something. And now, within our ansatz, we just impose that it be of OPE form, and we get an answer. Okay.
Use already regiments to reduce to this short.
No,
Oh, not yet.
not yet. No. So let me mention briefly the Reggie limit now.
But you're not using the detailed structure of these E's then at all?
Not even. Yeah, not even.
I mean, you didn't need to know what E was at all.
That's right. No, you can then go back and actually check. We also do some various consistency checks that it's really this sum with the correct form of the anomalous dimension. But we didn't even need that to get the symbol that we're interested in.
So the conformal blocks is the conformal group, the SL2, which is kind of orthogonal to the T and the.
That's right. It's the SL2 which is preserved by that square.
Right.
Yeah. Sorry. It's the. It's the SL2 which is preserved by these two light-like lines, I should say.
Is that
So
observed to all loops?
no. So at some point you will expect that this. So maybe.
Does the flux tube break the?
Yes, it does at some point. You would expect that you would expect not to be able to use this form at some point. That's correct. Now, for the leading discontinuity, I think you're safe to use that for all loops. But at some point, you're going to have to face the fact that you can't organise the sum in terms of those conformal blocks. That's right.
But that differential equation then just came out of some crude knowledge that you have of the curly F.
Exactly, yeah, some very crude knowledge that we have of, well, crude, I mean, just the fact that it's a conformal block, that means it transforms with certain eigenvalues under applications of the Casimirs of that group.
So that's invariant.
And
This
here,
is the Casimir.
yeah, exactly, and this is what that operator is doing. Okay. So let me just then mention in very briefly about the Reggie limit. So you can actually also analyze what happens to the symbol in the Reggie limit, and it turns out.
Just ask another question.
Yeah.
So that differential equation involves tau, which is really B under coordinate transformation, but the sigma and the rho, sigma and the phi, they're also related to the other. V and W, U and W or something.
That's right. Yes.
In a similar way.
Yeah. Yeah. I mean, U and W depend on all three of tau, sigma, and phi.
I see. So you have to.
Yeah. So indeed, in practice, what we do is we convert this differential operator into an operator acting in the U, V, W variables because that's more convenient for application to the symbol.
Yeah.
And it's not so difficult actually. And then given that operator, it becomes trivial to apply it to the ansatz that we're interested in. Okay. So then there's also the issue, you can look at a specific limit. With the multi-Reggie kinematics. This comes in two flavors, which I'm not going to distinguish too much, but you can look at the 2 to the 4, 2 to the 4, 2 to 4 limit, or the 3 to 3 limit. These are two different analytic regimes for this scattering amplitude. So what's the actual limit? The actual limit is where you take u goes to 1, but it goes to 1 in a sort of funny way, so denote it like that, and that means that you first analytically continue around the origin and then you come back to 1. While v and w both go to 0 in such a way that the ratio v over 1 minus u and w over 1 minus u are fixed. So in the limit you get a 2-variable function from the 3-variable function. And what happens to the function in the limit is following. You obtain you obtain a 2 pi I, and the reason you obtain a 2 pi I, if you didn't do this analytically continuing around the origin and then going to 1, you would obtain 0. So by analytically continuing around the origin, what you're doing is you're considering the discontinuity of the function across the branch cut starting at u equals 0. So a discontinuity then comes with a factor of 2 pi I. And then you have an expansion of divergences, of logarithmic divergences, in the limit as u goes to 1. So logs of 1 minus u multiplied by some functions of the remaining variables, g, r, l, x, y. And if you're an expert in regiology, such as Laboratoire and his friends, then you can, in a way very similar to the analysis of the OPE actually, you can write down formulae which even involve the same anomalous dimensions that appear here, and you can make predictions for these functions gr, which appear at, well, and you can make predictions at various orders in this expansion. The easiest one, of course, is the highest power of r, the leading log. But then there's below that, there's next to leading log and next to leading log and so forth. And in fact, the symbol that we find, F1 and F2 both vanish in the limit under question. So our two arbitrary parameters actually drop out of the symbol, which therefore means that we get a prediction at 3 loops for the symbols of the GRLs. GR3, because we're at 3 loops. So we obtain the symbols of these G functions. Okay, so in particular that actually allows us, for this 2-variable function, it's actually not too difficult to write down actual functions of human form, products of single variable functions that you can handle, which have this symbol. So we can actually write down this function up to a couple of undetermined parameters again, and the reason we have undetermined parameters this time is because now we're passing from the symbol back to the actual function, and that comes with its own set of ambiguities. In particular, every time I took a d, I missed some transcendental constant of a particular level. So I don't see anything that's like pi squared times functions of 2 degrees lower. So that's
Some addition of collinear limit cannot fix this.
well, so of course we would fix it entirely if we knew what R63 was. Okay, so that's one way you can fix it. Another way you can fix it is you can go and look at this Reggie limit in the light of this knowledge, and you can actually figure out what the Reggie expansion is predicting for you as you go to u goes to 1. And indeed, then this is what Laboratoire and collaborators did. And in so doing, they confirmed the symbols that we got, but they also managed to pin down for the next to leading log, they pin down our arbitrary parameters. But so far, I don't think anybody's done anything for next to leading log. But we also have a prediction there, of course, for the symbol. Okay, very good. So maybe it's worth just saying a couple of minutes something about the, so that was for MHV. What happens for the next to MHV ratio function? And there actually we can do even better, which it sort of is partly due to the fact that since it's a 2-loop problem instead of a 3-loop problem, you can get a sort of a better handle on degree 4 functions than you can on degree 6 functions, or somehow easier to manipulate. So there, we find the sort of this following form. So we find that the even part, the v function, is given in terms of essentially 9 arbitrary parameters. I write alpha x here because it's an overall normalization, which is indeed fixed. But it was convenient for us to fix this in another way, which I'll just say in a minute. But so there's some ambiguities, there's some class of ambiguities. More in this case than in the MHV case because the constraints of symmetry are weaker. And we also find a corresponding symbol non-zero for the odd part. And moreover, the parameters of the ambiguities in each case, there's no new ambiguities associated with this. So fixing this fixes that. And the reason that the two things are fixed to each other is because there's a constraint which is not parity invariant at this level. And that constraint is to do with the fact that well, they're erased now, but we had these prefactors which were given in terms of these rational R invariants, which I denoted as antisymmetric 5 brackets. And those things contain spurious poles. So they contain unphysical poles. So it must be that the functions are such that the final amplitude does not have those poles. They must have zeros at those locations. And the notion of a spurious pole is not a parity invariant notion. So it actually mixes up. The constraint involves non-trivially both v and v tilde. So that's why the two are tied together. Okay, so that's more or less where we got to there, but now we can even do better in this case. In this case, since these are degree 4 symbols, we can actually recognize functions for all of the above symbols. Most of them are simple products of simple single variable functions, so just LIs or similar, logs and LIs and so on. And a couple of them involve other functions that we happen to know, which are related to loop integrals. In particular, the things that show up are finite double pentagon integrals. So these are just these are double pentagon integrals with particular numerators that render them infrared finite. These things came up a couple of years ago in the study of Arkani Hamed and collaborators. We were also investigating their form. The point here is that they satisfy differential equations. And the fact that they satisfy differential equations, so this guy comes in sort of 2 flavors. There's a piece where the numerator in both integrals is of the same parity, and the piece where it's of opposite parity. The guy where it's of opposite parity. So these are 2 interesting functions. We denote omega and omega tilde. And these loop integrals, they satisfy differential equations. And the differential equations then are relatively easy to solve. You can write down the symbol, you can get the symbol of these functions, you can write down an integral formula which captures these functions. So these functions show up here in this expression. together with simple pieces. Okay. So now what we can do, given that we can actually write down a function, of course there's still all these ambiguities, and indeed there's even more ambiguities because now we should also parameterize all the beyond the symbol ambiguities, so all the terms proportional to pi squared and so on. So we write them all down. There's a handful of parameters left over, but it's an actual function with a bunch of parameters. And now you can compare to another representation. We took the representation due to Kosowa, Royban, and Vergu for the even part. So this V function, basically, of the 2-loop next to MHV amplitude. And one can even then just simplify. It's very convenient to use special kinematics where all the cross ratios are equal. You can take that, you can expand this for large and small u. You get an expansion in u in these regimes. And it has to match these functions. And now it's very non-trivial, but you can fix this handful of finite number of parameters with this entire function. So it's a non-trivial check that we can match a whole function consistently. Okay, and so we were able to do that, and we were able to pin down the values of all these parameters, and therefore give an explicit expression for both v and v tilde. And since it's kind of nice, let me just schematically give the form that you have something like v plus v tilde is some combination of omega and omega tilde, plus what we call simple being things like Li4s of single variable arguments and so forth. So standard single variable functions. So these two loop integrals, they give you really the non-trivial, the more complicated, or the piece, if you like, the piece of the symbol which actually depends on the y's being the variables which couple up the three variables to each other. Moreover, you can actually write a formula, an integral formula. When I say we have the function, this is what I mean. And for the differential equation that we have, can actually write down an explicit formula. So this is one particular version of it, which is quite useful. Where this integrand, this q phi, is a degree 3 function which can be entirely expressed in terms of single variable functions, products of degree 3 single variable functions. So I think I would claim that for single variable functions, the natural basis of functions are harmonic polylogs, a set of iterated integrals over kernels, which are, in the useful ones are just, in this case, are just 1 over u, 1 over 1 minus u. You iteratively integrate up these. And I think to generalize to the right class of functions that we want for the 6-point amplitude, I think we should write down formulae like this. So I would propose to sort of define a class of functions that use these kinds of formulae. So in principle, you could also choose some basis that you like and then work hard and re-express this in terms of some complicated sum of Li, M, N, P, whatever, multivariable polylogarithm functions. But I'm not convinced that that's necessarily the right way to go. Okay, and well, I should basically wrap up now, but let me just advertise one final point, and then I'll stop. So we sort of, in this approach, we've sort of come across some nice integrals, some nice integral representations for the loop integrals, such as that. Turns out that we can also obtain a new version of the two-loop remainder function, which Nastya described in the previous talk. So going back to two loops for MHV, we can write down a formula for the two-loop remainder function, which involves these finite double pentagon integrals, which have this non-manifestly single variable function expression here. Of course, we know from their work that the two-loop remainder function can be rewritten in terms of single variable classical polylogs whose arguments contain square roots and so on. However, you can analyze the symbol both of the three-loop remainder function and the two-loop next to MHV ratio function. You just look at the symbol, you can do the same kinds of operations that they describe in their paper to check, can you write this in terms of classical polylogs or not? And the answer is not. So we know for sure that those functions cannot be written in terms of, even more generally, products of single variable functions. It's not possible to write those things in terms of products of single variable functions. They're intrinsically multivariable objects at three loops for MHV and two loops for next to MHV. So in that case, what we hope and propose maybe is that actually this formula for the two-loop remainder function is the kind of thing which should generalize. So this is a formula now which disguises the fact that actually you can rewrite this in terms of single variable function. But we know that you can't for higher loops, so maybe this will generalize. Okay. Okay. So just to summarize, then we've managed to pin down using this kind of bootstrap idea, essentially the symbol of the three-loop remainder function up to two free parameters. Those two free parameters were all then fixed by Simon Caron-Hur and Song Hei in their bootstrapping paper from December using this Q-bar equation. So I think we now know the values of those two parameters, and therefore we know the symbol of the three-loop remainder function. The fact that those two approaches landed and were consistent with each other is a very convincing. So we have that. We have an analytic formula for the two-loop next to MHV amplitude, which I presented. Particularly the odd part, this v tilde function is non-zero starting at two loops. So this bootstrap method and the constraints that we impose, they know about it, and they force it to not be zero, and they even pin it down. So most generally, kind of questions that you might ask then are, is this approach sufficient? So are pure functions going to be sufficient to describe the scattering amplitude at arbitrary loop order? And we don't know, of course. There's some indications to suggest that for high numbers of legs, for high MHV degree, there will be more general functions appearing. So it will be very interesting to know at what point this kind of ansatz should break down, or if it does, or if it doesn't. In particular, we know that the 4 and 5 particle amplitudes, as far as we are aware, do not contain any data that looks like it could come from some non-pure function. In fact, the kinematic is very simple. It's just logs and dilogs. But then there's also a particular number at each loop order that's multiplied by. And from this integrability story for the cusp anomalous dimension, this function of the coupling which appears as a prefactor, we know that at each loop order that's supposed to be some zeta function, some zeta value of the right degree, or products of zeta values of the right degree. And zeta values, they're specific values of functions in this class of functions. So there's a puzzle, if you like. There's a puzzle if the scattering amplitudes at high loop order, high numbers of legs, want to contain new objects. how is it that they disappear by the time you get down to 4 and 5 points? So it would be very nice to know if that's possible or what the resolution for that is. Okay, so I think I should probably finish there.
Thank you. Questions?
Any ideas on the... Oh, sorry. No, you go ahead.
You mentioned the single variable functions. Sorry, I probably missed that.
Sorry, yes. So I didn't explicitly define them, but so there's a nice class of functions called harmonic polylogs. So whenever we see something, a symbol that only contains these rational entries, u's and 1 minus u, then we know that we'll be able to express that. That will be the symbol of some function which is given by a harmonic polylog. And the harmonic polylog is something that's defined in terms of, well, it's something that's defined in terms of some word, depends on some variable, x, and the word can be made up of, in this case, zeros and ones. And if the word is a string of zeros, k zeros, then h of this string of k zeros, x is 1 over k factorial log x to the power k, and otherwise it's, if I append a 0 or 1 onto that, then it's the integral up to x ut over, and then if a is 0, then I put t in the denominator, and then I integrate the function with the word w, so that's a is 0, and if a is 1, I just replace t with 1 minus t. So that defines iteratively a class of functions, single variable functions. Their symbols are always x entries x and 1 minus x. So when I say simple, I mean this class of functions, single variable functions, or products of those. So that's what simple means. But then in addition, there are these things which intrinsically involve the y's, and there you have to use formulae like this.
More questions?
If you want to add more points, the key thing to understand is how to generalize the list
Yes.
we have there.
So, okay, so, right, so generically, for a higher number of points, rather than using these 2 brackets, it's maybe better to go back to 4 brackets. And then for the 4 brackets, you must also allow yourself to consider things like intersections of new points defined by intersections of lines and planes and so on in twistor space. So you'll have all the 4 brackets as potential entries, and then all 4 brackets also allowing yourself points defined through intersections, new points defined through intersections of data constructed out of the original points. It's just that at 6 points, all that stuff collapses back again into stuff that you can re-express in terms of those basic quantities. So for example, I think the symbol, Simon's symbol for the 2 MHV but arbitrary number of points contains entries that are constructed out of things like that.
Any more questions?
When it says maybe this will generalize, in which direction are you trying
Oh,
to
I mean this formula, so I think of this as a formula for the function, for the remainder function. So when I say maybe this will generalize, what I mean is maybe we'll be able to write the higher loop remainder function in terms of functions like this. So in other words, in other words, yeah, higher loop. Yeah, I mean higher loop. Yeah.
I mean sometimes say you're not. This q is a function of one variable object. Is that?
Well, a product of single variable objects. Yeah.
Is this not somehow because you're going from 4 to
Yes.
3?
Yeah. Sorry. So I should have been more careful. I mean, I would. So that was in this case for omega 2, but more generically, I'd expect to have here some q, which is again in the class of function.
What I mean is it? I mean, if you're going from transcendentality 4 to transcendentality 3, is it not the case that transcendentality 3 is so simple that I can always write it as a product of single variable functions.
That's correct.
I thought I wouldn't necessarily expect this to generalize to higher loops because then I go from.
Yeah, that's correct. When I say single variable functions, that was for this specific example, omega 2. But more generally, I would expect to be able to write down a formula like that, where this is again in the class of functions that I'm interested in. So it could be itself defined through an integral formula of a similar kind.
More questions? Not then, let's thank James again.